Hi everyone. Yeah, it's my pleasure to be here today to show you what we have new for the next release in 2024. But before we start, let me just give some announcements and here some disclaimers. So everything that you're going to see during this presentation will be delivered to you with the next release. As you can see there, CST is scheduled to be released on November 18th. So by this Saturday. So yeah, just hang on. You will have access to those features quite soon. Right. And as many other major releases that we have, there's always more content than actually time to present it to you in a very short time here. Therefore, I would like to invite you for our electromagnetic days, which are scheduled for February, so beginning of next year. And what is these electromagnetic days? So it's basically 2 full business weeks packed with electromagnetics. And you see there, we have dedicated topics organized on each day. And you can be sure that we are working very hard to deliver to you the state-of-the-art simulation content. Um, this link will be then posted to you here in the comment section so that you can click on and register to the sessions as you and have a little bit more look on the agenda as the things get prepared. And yeah, with the informational stuff out of the way, we can start with our current talk. Good. So today I've separated to you some highlights for our high frequency applications. So in specific antennas and RF component design here. Some highlights for our high frequency solvers, and then we will have a quick look on on our Python interface in regards more to the Python automation that we can do now in 2024, which is a quite exciting topic for me personally. And also last, we will see some nice news about cloud computing and 3D experience platform. Okay, then starting with antenna and RF components. So I want to start here with talking in general about antenna arrays. So we can see here how our workflow is organized. And in particular, we have been focused on strengthening our solutions for MIME arrays used basically in base stations. Although most of the functionalities that we have developed can be applicable to any other classical phase array, right? So some highlights that we have in here first is that there is a number of things that were enhanced in the array task. And if you're not familiar, the array task is the tool that provides the modeling and the automation of array simulation. There we have a very good speed up in the creation of large array models. And then also T-Solver now supporting multiple excitation lists to be executed in a sequential way. Then regarding the simulation of these very big arrays and models, we have the DDM solver. And the DDM solver has some significant improvements, which I will talk about in a couple of slides. But first, let me just show you a minor feature that might interest some of you. So whenever we create a unit cell simulation using the array task, you are prompted to this dialog box that you see here on this slide, right? So what it does, it will define the parameter sweep for the calculation of what we call active element pattern. However, sometimes you might be interested in getting some quick results. Let's say just a lower fidelity result or lower fidelity pattern is pretty much good enough for your job, right? Then you can combine it later on with the array factor. And now is it possible by, if you check this checkbox here now, Studio will create this low fidelity far field, let's say like this. Uh, that is not as accurate as I must say, there's not as accurate as the active element pattern, but that doesn't require also the angle sweep that we define here, which might take some time depending on the case, right? So in the end, um, this is a better solution. I mean, it's better to use this low fidelity pattern than actually using an antenna in isolation when you're doing your quick estimations. Of course, all the benefits that you have with the array task, for example, the array factor with the dynamic excitation list, these are also still applicable here. Coming to the domain decomposition, as I said before, so there's a lot of work that we have put into this solver here, especially for this release, and we can name a couple of things in here. The first of all, is the scalability that has greatly improved. So, especially for the load balance here, uh, when we make efficient use of the hardware available. So in the past, if you have used this solver, you could get some memory spikes that would cause unexpected crashes, which for the newer version, this should not be the case anymore. And on the right, you see here one of the examples that we have solved and how the parallelization of the adaptive mesh refinement impacts the speed up on a 40 core machine. The domain decomposition is also, of course, well suited for MPI calculations, and therefore much work has gone into stabilizing and make it viable now with good scalability on MPI for larger models. And in general, it's just a more robust solver at all, right? So as an example, so we have here a base station that is a shared aperture here with two arrays, one stack on top of each other here, and they're covering basically two bands for the LTE and 5G. So this model, what we have run was a 68 port excited for one of the polarizations, and all the results that you're going to see here, they were executed on a single machine with 48 cores. And if we compare now the results for 2024 with 2023, we see that we get a nice 15% reduction in memory and up to 2.9 times in speed up on the overall runtime. Note that this functionality will actually become available for you in one of the service packs. So we don't have any results here that we can show for the MPI. So that's why please be tuned to the electromagnetic days, because, well, by then we will have things to show and better demo you for the new enhancements for the DDM. And on a personal note here, I work with these kind of structures every day. And um, it is quite impressive actually to see that the fact that we are able to solve such a model that has, let's say, 15 wavelengths in height with the full geometrical complexity of the radiators in a one single machine. This is quite impressive feature, I would say. And on the contrary, if you work with these kind of arrays in here and you run simulations with simultaneous excitation workflow, for example, where you will get only one result. What we are getting here with the DDM is actually the full less matrix in the end, right? So we're talking here in this case is 68 by 68 matrix in a very respectful 5-hour simulation time. And this is all for the broadband results, right? Covering the entire band. If you're just interested in a couple of frequency samples, there we are talking about half an hour per frequency sample. Right. So then coming to antenna megas, you can now evaluate the performance of different antennas, I mean, different variations of your same antenna there with respect to some selected specifications. So let's say if you have one antenna that has a couple of variations in relationship to, let's say, the substrate here in this case, right? So we have the KPIs here being listed on the center of your screen, and then we can see how the individual KPIs are scored for those specifications for the different designs. And on the top, you can see the overall scoring of those designs. Moving forward with non-parametric optimization, this is a feature that we have introduced in 2023, but in 2024, of course, has a lot of enhancements that I want to show you here. But just to put things into context here so that everybody knows what we're talking about. When we have non-parametric optimization, we are talking about two different strategies. The first one is the topology optimization, And what we are willing to do in the topology optimization is we define a design space, a sheet, or a volume, and we want to find a function in it, right? So we give that space and then we put it to the optimizer, and then it will find a structure that will suit your requirements for the optimization. So what you will have in the end is if you have a meshed, let's say, surface in there, you will have inside of the mesh in there certain points that will be filled with the, let's say, the support material or the original material, or the material that is specified as a filling material. So for instance, like a pack, right? And this is a optimization that was previously available for high frequency, but we are seeing now promising results and good results on the benchmarks that we have done for high frequency applications. For the shape optimization, on the other hand, what we want to do is to achieve high performance. So we start from something that it's already working. Then what we do is specify an area, something like this, from that specific object of a specific antenna, for example, that we will show later on. And what we do, we warp the geometry. So we change its shape so that we can achieve a maximum or minimize some other goals that we have for this optimization. Okay, so two different strategies to keep in mind. So the first example is regarding the topology optimization. So we have here ultra wideband example, and what it is we defined a metal sheet over a finite ground, and this metal sheet or the design space there is fed by a coaxial connector that comes from below, and we put as goals it for the optimizer to have radiation over ultra wide bandwidth. And then you see here below, we have an antenna that's also performing with the same specs that we have generated using antenna megas. And it's quite interesting to notice if you see that the direction that the topology optimization actually goes resembles pretty much what we have there from antenna megas, right? So this rounded bottom of the antenna that gives us a matching over the wideband. And if you look at the results, we see that there's a great input matching in there over the entire bandwidth. We're talking about a decade of bandwidth here with a total radiation efficiency that is above 86% over the entire bandwidth. Moving towards the shaped optimization. Um, One thing to note here is that now their far field design response supports Ludwig 3 systems, which drastically simplifies the goal definitions for far field manipulation, far field goals. And it's also possible now for the mesh to make larger movements, like and ensuring still a good mesh quality. And this means that we were going to have better results. Like for example, here we have this smooth wall horn antenna. So what we start with, we take one antenna from antenna megas that uses an exponential function for this inner wall of this horn antenna. Uh, which typically outperforms all the lower order functions that is given, I mean, for antenna of this size here. Now, without setting up any complicated parametric optimization, like setting up a higher order polynomial there to be optimized, we simply select the face in there that is our designing space that is now highlighted here in green. We put to run in our optimizer with our shape optimization, and then after only 28 iterations, we already have a highly performing, radiator with a really nice cross polarization over the entire bandwidth that we want. When it comes for the filters, I just want to show this very quickly for you here. We have a new workflow for the low pass filter designs, and this is how the workflow would look like. So first of all, you enter the specifications of your filter for the basic transfer function of a low pass filter. Then FD3D will then synthesize the ladder circuit that would give that response for you. And then to implement this circuit at a high frequency in a 3D model, the equivalent inductors and capacitor components are designed. And here the partial RLC solver is used to generate the design curves of each component. We will see an example right away. And then the model is automatically built to you with those blocks, similarly to what we would do for our bandpass filters. And last, with the optimization step using the FD3D with the automatic extraction of the feature based on the synthesis there, we get a very nice um, tuned response in a pretty much a few iterations in that we will see here next. So here is just an example. So you can see what is the design that we are willing to achieve and the ladder secret that it was generated, the different components that are analyzed using our partial RLC solver and their respective design curves. And then this is all put it together, and then using the optimization with the space mapping in there, we have a convergence within only 5 full wave iterations. Talking about bandpass filters then, I just want to highlight one of the things in here, that it's the addition of some components in there. So we're talking about non-radiating nodes and resonant couplings for the topology and layout step. A non-resonating node is typically used to introduce transmission zeros and an inline topology with what's so-called dangling resonators. So you can see here that we have these um, transmission zeros, which are typically produced when we have cross coupling between the elements. And this kind of topology here is pretty much very attractive in waveguide filters where it might be impractical to do those cross couplings, right? And with the space mapping optimization, again, we get a very nice convergency of our optimization in only 19 full wave iterations. Okay, so moving on to the solver highlights. We will start with talking a little bit about the F solver. So I think the biggest highlight here for the F solver has already been mentioned and talked a little bit in detail. That would be the domain decomposition solver improvements that we have. Just want to encourage you to use this solver. It gives your feedback as well. I mean, the DDM solver is especially useful for antenna arrays. I mean, that's our tests that we have done. However, I mean, it can benefit many other applications in the workflow. So yes, please make note of that. And also we have some major improvements also for the Think panel support in the F solver. So now it's in general much more robust material. So it now requires basically no additional effort from the user when we are handling complex models that might have some complex interfaces, when the Think panel might overlap with other materials like, I don't know, PAC or whatever you have in there. So in the past, um, we would have to resolve the mesh of those interfaces, and now this is automatically and transparent done for you, so you don't have to worry too much about it. um, and and also there's some new options for solution storage now. So this might spare you some gigabytes of disk space when saving our models, especially useful when we're working with larger models, like with many ports and results, right? With the T-solver in here, just want to make a quick mention about the improvements. This is more like an incremental speed up that we have with the new solver, in the newer version with the T-solver, when it talks about the GPU acceleration. So you can have a look here. It's an additional speed up that you get only by upgrading your studio version to the newer version 2024. Um, but here as well, we have some small features on the MPI side in there for considering only the 0D and 1D results when doing the download and merge of results here. So we're talking about MPI, right? So this option will also apply to other solver data like large material and hex mesh files uh, that might take a lot of disk space. So if you only consider the 0D and 1D data only, so you don't have to download all those big files to your machine or to whatever, and this might also speed up a little bit the time for download and merging time, and also reduce the size of the data to be stored. Coming to the integral solver, I think this is a really nice feature and really interesting ones. Like now we have the support for even higher solver order. Okay, so this feature is very useful when we're dealing with large structures which are fairly flat surfaces. It's where you can definitely unleash the potential of these, let's say, larger surface elements using the higher solver order to reduce the amount of mesh elements while still keeping the same accuracy. I mean, it might sound a little bit complicated, so let's take a look a little bit on one of the examples. So we have here a dual reflector antenna with its feed, and you can see that on the top there we are using this higher mixed order. So we have there on the main dish uh, like big elements, big triangles that are using this higher order solver. And when we talk about closer to the feed, you can see there's a lot of more triangles in there. So would be the lower order mesh, but it's still uh, being accurate enough. I mean, the whole thing here is to have everything meshed adequately with the enough precision that you have in your solver order and mesh accuracy without sacrificing on the solver results. And you can see here that we save a lot of mesh elements. We are talking about a factor of, I don't know, one order of magnitude in there. But more impressive there is about the timings. So not just on the memory, but the timing. We're talking about solving the problem in 2 minutes instead of 1 hour here in this case. And just to prove that this is still a very accurate result, we have here a comparison showing that both results with the first order elements and with the mixed order solver, there we have like a pretty much the same results for the far field for this example here that we have shown. Okay, so coming to the A solver, so I must say that accurately calculating diffraction using the asymptotic methods or ray tracing is not very simple. And I'm quite glad to see that now we have done a very important step by introducing the uniform theory of diffraction in CST, so in short UTD. And UTD greatly improves the calculation of diffracted fields on sharp edges, for example, as you can see here on this picture. So on the top, what you see are the fields. When UTD is not enabled, and then you can see that pretty much behind that wedge, we have a complete total shadow of fields. And then on the bottom, when we activated the UTD, now you can see that the shadow region being filled by the diffracted waves by that sharp edge. And you can imagine that depending on certain applications that might increase uh, tremendously the accuracy of the results. Continue with the A solver here. We also have a higher order PTD or physical theory of diffraction calculation. And what does it mean? First, like let's just make clear that the UTD that I mentioned in the previous slide and the higher order PTD are two independent features. Okay, so the normal PTD, what it does, it calculates the fields only when the edges are illuminated directly by our source. Okay, the higher order will then get the diffraction of the from the edges that are also indirectly illuminated. And by indirectly, I mean rays that bounces through other surfaces inside of our model, okay, or even UTD rays if UTD is enabled. So like, yeah, it's a little bit complicated here with the wordings. There are too many TDs there, but here on the picture, I think it will make clear, right? So what we have here on the picture, you see there on the bottom, we have one case where the ray is pretty much scattered from the surface, and then that scattering of the surface hits the edge of this triangle, of this geometry, and these rays will be then diffracted using the higher order PTD. right? So it's an indirect heat of the edge. And on the top there, we see one ray that it is diffracted using the UTD solver now. And then one of these rays that are diffracted will then hit another edge, and then that ray that hits the edge will be the diffract again using the higher order PTD as well. So um, more diffraction in there that we have in our models, the higher the accuracy we might get as well, the better the accuracy in many applications that we need to have. Good. Uh, Moving to the hybrid solver. So what we have here in the hybrid solver task is we have introduced a new workflow that for the unidirectional that we creatively named unidirectional advanced option. And this new advanced option, what it does, it boosts the performance of those applications for which the bidirectional coupling causes maybe too much simulation time, but also for the normal standard unidirectional approach, it's not accurate enough, especially when we talk about S matrix calculation, right? So if we recall a little bit, what the standard unidirectional does is it will calculate the fields on the source models in there, record the fields on the bounding box, on the boundary box, and then it will couple, or it will then couple these fields to the larger simulation, to the platform simulation, to see yeah, the unidirectional coupling in there. And then the S parameters would be calculated using reaction integration. Okay. On the other hand, a bidirectional approach is an interactive calculation that will exchange information between the platform model and also the source models in order to get a full accurate S parameter. And then you can think about, because it's interactive, it might take a little bit time to converge the results. And then this advanced option sits exactly in the middle there. Is where we have the improves, and we will see a little bit more details when is the cases to use those. So the workflows that could benefit from using the unidirectional advanced would include examples where, for example, we require to calculate the biohazard or SAR values on receiving domains, like you see here on the right picture, or coupling between antenna arrays, as we see here on the left, or the receiving S parameters for platforms when we are using FIT, TLM, or F solver. So you have noticed on the last slide, I place here which solvers can be used for the platform simulation, and then the unidirectional advanced is a little bit more flexible in terms of the solvers that it actually supports. Here, just some benchmarks or some numbers to encourage you also to test the new unidirectional advanced hybrid solver there. So we see here the calculation for the bidirectional simulation using only 2 iterations, 40 minutes in there in comparison to 14 minutes with the advanced, and the other example 15 minutes in comparison to 23 minutes. So yeah. And last one that I want to talk about, the improvements in the performance, is about our interference task. And this is something that we have um, in recent years worked a lot to improve its simulation performance in here. And I mean, just take a look at those systems, right? So what we have here, we have 6 transmitters and 4 receivers, with some of them having thousands, 10 of thousands of channels, right? And you can see there on the table on the right the progression, how this it goes. Like yeah, we started from not being able at all of solving such a big system in version 2022 to being able to solve it, but at the expense of a pretty good workstation, to now being able to reduce it to and being simulatable, let's say, on a single laptop. So we're talking about memory consumptions there that are not higher than 1 gigabyte of data there being run in under in 2 hours and 7 minutes here for this case. Okay, good. With that, we move to our next part of the session, that is talking about our Python automation. And then this is another topic that we have actively been working, and I'm quite involved as well in the Python integration and automation there. So, and it's something that we have been improving over the years, right? So just to put a little bit on the context here, before we initiated this project, all the access to Studio was done via the COM interface. That was pretty much common to everything that we want to do externally, right? That be MATLAB, Octave, or Python, right? However, after seeing the benefits that tighter integration with Python would bring to our customers or to our users in general, we have launched back in 2020 our first version of our Python interface. And back then, it was a pretty much a minimum package with support only to a few libraries and a single Python distribution. But for 2024, we have massively increased the number of supported distributions for Python that we have, also extended our libraries that are available, and we started also making our old VBA methods available natively in Python as well. So here is a video demo of the current state of the Python interface, which I will not have time here to go on its entirety here now. But if you just notice, this is supposed to be, I mean, this Jupyter notebook is supposed to be a tutorial about the Python interface, and this will make available to all our customers in our knowledge base soon. Okay, so let me just show a little bit what I mean about the different functionalities in there. So let me jump a little bit ahead. Um, so we have here, so if you see, I mean, if you are used to work with automation and creating things on, we're using VBA, you will recognize this store double parameter here. It's actually a VBA method that now can be called directly in Python. Similarly, if we move forward here, we have the possibility of placing ports using the script. And this was also another example of uh, a, a operation that we could only be able to do on VBA. Also, the possibility of setting up as parameter tasks, for example. So this can also be now natively being called in Python. And last here that I want to show you is that also we can now, for the ASCII export now, we can trigger it directly here from this notebook. So this makes a lot easier, I would say, to work with the data when we do make the export here and we trigger the export. Like if you want to manipulate the fields, for example, let me just move a little bit forward. Let's say apply some phase changes or whatever you want to do with the fields. You can manipulate those now in code using Python, and also later on visualizing as you will, also using Python. So quite nice additions and quite nice extensions of our Python interface. Just remind you that this Jupyter notebook will be available for you soon in our knowledge base. Good. So one thing that we'll right away notice when you open Studio and then you have a look there on our taskbar is that in 2024, we now have a Python button close to where our macros used to be. So the old macros are now organized under these VBA macros, and besides the name, basically nothing changed there. But under Python, you will find CST apps and run scripts. So run scripts is basically where you can place your own scripts for easy accessibility. So it's quite easy to set up. You just need to add the library path in the CST settings, as you can see here on this slide. And the scripts can then later be further organized inside folders, and those are displayed as subcategories, I might say like this, in the drop-down menu. CST apps, on the other hand, it's where we will organize all the codes that are directly supported by us. So currently, there's only a couple of scripts that are dedicated to the EDA workflows that are present there, but more functionalities will be added as we develop them. So yeah, stay tuned for for additions that might come with service packs and new releases in general. So proceeding to Our last topic of the day, let's just have a quick look on some new capabilities when we talk about cloud computing. First is the addition of new hardware, right? So now you have the option to run your models in single node with up to 768 gigabytes of memory. So, or even let your bigger models run on a multi-node MPI configuration with up to 2.8 terabytes of RAM. Um, These including, I would say, all the options that we have with GPU acceleration should be more than enough to tackle the vast majority of the models and simulations that you might have. A further extension of our cloud computing capabilities is that now cloud can support a schematic as well, which also includes the hybrid solver, which we could do this already in the last release, but now it's much further enhanced and stable. Then you can see here in this example is a very simple schematic execution. We have just an antenna with just a port and a resistor being connected to it. This model is then saved and loaded to the 3D Experience platform. And from the simulation manager app, you can launch the simulation, and you can see there the options there for the cloud computing to be run. And then it's like, yeah, now the simulation here will run. And then after the simulation is finished, you can also launch CST directly, also using the simulation manager app, so that you can visualize the results. So you see here what it is doing is Studio has been open in your browser. So it's the connected version of CST, like it's the cloud version of CST. Sorry, not the connected, but the cloud version of Studio that it's open in your browser, so that you can visualize now your results. As we see here with test parameters on that were calculated on the schematics, DC combined results, but you also are able to work with our model and set up, like, let's say, further post processing if it's required. Right. All your all this on your browser, right? So there are still some limitations to what is available on cloud. Here we can see, let's say, a more comprehensive listing of what it is currently available. But I think the important two takeaways in here is one is 3D modeling and 3D solver are supported on both cloud, front end, and compute. Um, and I mean, at every design cycle, or at every development cycle there, we are removing the limitations that we have with the cloud. So if there's anything that you have in particular, a workflow that you should be covered with the 3D Experience Cloud that we currently cannot do, please contact us, and then we can have a look at those. And to give you a glimpse of the roadmap as a whole, distributed computing is the next milestone that we have for the cloud computing, and this you can expect to be available soon. All right. And with that, I can close to the end of my presentation. But before we can open the session for QAs, I just want to remind you about our next update webinar that will be on December the 7th. And it will include the highlights for electrical machines and low frequency applications, as well as EMC, EMI, and EDA. And please don't forget to check and register to the Electromagnetic Days next year. I will leave this slide here for a couple of seconds so that you can grab the, no, actually the link will be posted for you again there on the comments, on the comment session. So have a look at it, check the agenda. Yeah, I mean, good things will go from there. And I hope this session was informative to you. And if you don't stay for the QA until the end of the QA, I wish you a great day.